I'm an active astronaut. I just finished serving 2 years as the chief astronaut there at the Johnson Space Center at NASA, and I'm transitioning now. I handed those duties over to my colleague, and now I'm transitioning to getting ready to prepare for another space mission. I went to the space station on my first mission on a space shuttle for 2 weeks, and the second time on the space station I lived there. And comparing those two, it's kind of like comparing a vacation home or a hotel rental room to your own home, in that in a short-term rental you don't really care so much about how well the hot water heater is performing or how the air conditioning system is running. You just make it colder or you make it hotter, and it's not your problem how it's functioning. Whereas in your own home, you care very much how the air conditioning is working, how the sprinkler system timing is set, and all those details. And so you really feel some ownership when you're there for 6 months, and that's how I felt. After I got comfortable, maybe a month into it, I felt like it was my home. My first mission was on a space shuttle, and it was summertime in Florida, which if you've ever been there, there's rainstorms, thunderstorms that happen every single day. And why we ever try to launch a spaceship in Florida in the summer is beyond me, but that was our case. So we were supposed to launch in June. We ended up launching in the middle of July after 6 launch attempts. 3 of them we had just woken up and were eating breakfast and we learned, so we hadn't even really done much of the day. I should mention that on the shuttle, you launch at the equivalent of about 4 p.m. of your crew day. It's not always 4 p.m. locally, but we adjust our sleep schedule. So you wake up, you have a full day of stuff before you actually launch. And that accounts for all the time it takes to get you strapped in and undo the launch pad prepare. Anyway, so the 6th attempt we actually really did launch. So the other 2, we were inside, strapped in, got to that 9-minute countdown, and they said no go for weather, and then you have to undo the process. It turns out the fastest way to get out of your spacesuit is to do it in space, because if you launch, you take it off about 10 minutes later. If you don't launch, you have to wait a couple hours for people to come back and rebuild the launch pad and get you out and drive you back to the crew quarters building. So on the day that I actually launched, I really didn't believe I was launching. And I like to tell people, imagine you tell your kids that tomorrow is Christmas. And then they wake up on that day and they're all excited, and you go, oh, no, it's not tomorrow, it's going to be Thursday. And then Thursday comes and you go, oh, no, it's not going to be tomorrow. We have a little bit of issue, it's going to be next week. And you do that. On the 6th time, the kid's like, this Christmas thing is a total hoax, it doesn't exist. And that's how I was with my launch, and I really did not believe that we were going. In fact, out the window, it was all cloudy and just didn't look like a launch day. However, the big final go, no go to launch happens at T-minus 9 minutes. And we came to that T-minus 9 minutes, and they go around and they're like, the flight directors go, range safety is go, weather, which is the one we cared about, weather is go. And that's when it hit me, like, holy cow, I am strapped into a rocket right now, and we were just given the go to launch. And short of a mechanical failure on an engine in the last seconds, we're going, and this thing is going to light. And that was really interesting. As a professional astronaut, you have a job and you're sitting in a certain seat because that seat needs somebody to do whatever task it is. So each of us has a role where we're following along whatever it is. In my particular case, I was called MS1, Mission Specialist number 1, just based on the seat I was sitting in, and I had a bank of computers right here, and I was supposed to follow some data on those computers, and if any of it went wrong, I was sitting behind the pilot, and he and I would then go to the right page of the procedures. The space shuttle was interesting. All the procedures were paper in actual books, and we had, I think it was like 17 different volumes, 17 different books. Each book was 1.5 inches thick with different pages. So depending on what the signature you saw drove you to a certain book, and then within that book, which tab to be on, and within that tab, which page to be on, and then further, what step to be on. So because of all that, we really wanted two people to agree, all right, I think we're in the computer book on page 17-5. It looks to me like we're in step 6. I agree, we're in step 6. And then it says to do X, Y, and Z, and then you kind of do that together. So we really did everything. I say did, the shuttle is past tense because we don't fly it anymore, but we really did everything as a pair to minimize mistakes. The space station has a little bit more automation in it, but to a large degree that you're following a procedure and executing. It is taxing to be on edge for 6 months straight, and that's, I think, one of the reasons why it's hard to do longer. Like Scott Kelly just did a year, just about a year, and we had another astronaut just land last month, Peggy Whitson, who was up there for close to the same 10 months or so. And it's not any zero gravity effect that makes you so tired and want to come home. It's the fact that you are on the pointy edge of an operational space station, and your actions can be bad or your actions can help, and you always are thinking, is what I'm doing right now going to make this better or worse? And also your whole day is scheduled. So it's this cumulative fatigue that makes it difficult to be there for so long. How do we help the scientists get good data is important and near and dear to us as individual astronauts. And so some of the ways we do that are set up a camera overlooking the experiment that we're doing, and have the radio and we're talking and directly to the team that the investigator is from, or perhaps in some instances to the investigator. In many instances, the experiment doesn't need tending to, it just needs to be set up or activated. Those kind of ones are easy for us. Maybe they'll be looking over as we set everything up and then close it and put it aside, and it runs for a month or whatever it does, and collecting all the data. And sometimes in that type of scenario, we'll be called, hey, we're not seeing the health and status as a green flag. Why don't you go check? And sure enough, maybe it needs to be power cycled or something like this. So it ranges from that type of interaction to very hands-on, where our actions are driving the reactions of the experiment, and so we really need to be more familiar with those kind of experiments. There's so much to know, and if you had to know it by rote memorization, it would be a lot of training. We probably would never get there, because right when you think you know it, you have to learn something else and you forget what you learned last month. That being said, we get trained at a pretty solid level across the board, but what we really count on are well-written procedures to run when we get up there. They are sometimes printed, but now with pretty much every procedure is electronic, and that's another thing, is how do you write a good procedure? How do you follow procedure electronically? When you have a piece of paper, you can check off steps that you've done, and we have a really nice procedure viewer that the line highlights what action you're supposed to do. And that goes a very long way to mitigating us making mistakes, because if we rely completely on our memory, we're going to make mistakes. And if we rely on kind of scrolling through an electronic page, we're going to miss steps. So it's evolved over the course of 15 years of people being on the space station, but we have a pretty good system now to help with that. And you think that procedure reading is just something that everybody can do, but I can tell you, I'm okay at it. There's a few astronauts, like Megan MacArthur is probably the best procedure reader we have in the astronaut office. She has just this amazing ability to read all of the stuff and read it out loud in a way that it makes sense, and it's a skill that takes some practice and some getting used to. Yeah, we don't have the luxury on the space station to put two people doing everything. Everybody's off all day long doing their own. There's certain parts of the procedure where you're just setting stuff up, and if you hook up a wrong thing, it's not a big deal until you turn it on. So somebody can back you up on all that, and people are through the video. But when I know that I'm getting to actions that are unrecoverable if you screw it up, I'll call on the radio and say, okay, Houston, this is what I'm doing. I've got X, Y, and Z connected, and I'm about to throw this switch. You agree? And so you can kind of use the ground team as another person. There were a couple that had some complicated setups. Inside the glove box, we had to put a lot of things, and cables needed to be routed a certain way, and cameras needed to be set up in a certain way. And it was kind of like a one-shot deal in the particular one I'm thinking of. It was a great deal of setup. One action was going to happen, and the data was the video and pictures of that action. When you're on the ground, your spine is all the way it's supposed to be. As soon as you get to space, the gravity is not pulling your vertebrae together, and every space between each vertebrae elongates a tiny bit. And you add all that up throughout your spine, and each person grows like an inch and a half from your waist up. And that, you notice a little bit of back discomfort when you first get there, but it's not very terrible. It's almost like a day of working in your yard that the next day you're a little sore. Coming back to Earth, I thought it was going to reverse that, and some astronauts have back pain when they come back. I was lucky and didn't have any particular back pain. The thing I noticed most was the lack of ability to balance, and all of the little muscles that work together to keep your core tight and strong, your back straight, they're all out of whack, and they're not working together, and it's difficult to stay straight up. It's difficult if you're standing to not fall over, and it takes a little bit of rehabilitation to get everything right again. We do a bunch of baseline experiment data collection before we launch, so they know what your level of performance is prior to going, and then you do those same experiments when you get back. In some cases, you do them while you're in space. You'll do one at, we call it L minus. L minus a year, ideally, L minus 6 months, L minus 3 months, 1 month, and maybe a week. But everybody wants something a week from launch from you, and so it's impossible to do everything in that final week. So it's usually a month is the closest they can get. And then you go to space, and then you come home and you reverse that. You do immediate on return day, if possible, a week, a month, 3 and 6 months later, and even a year after. So there's a whole spectrum of data. Blood, urine, cotton swabs in your mouth, you're giving a lot of your body. I even had a muscle biopsy in my thigh and my calf, where they took a thing about the size of a milkshake straw, you know, a little bit thicker than a normal straw, and jabbed it into my muscle and took out about an inch-long core of muscle sample, which was less than pleasant. Before we launch, we're briefed on the suite of experiments that are available to be a part of. There's not enough time in your crew day when you're up there to be a guinea pig for every single experiment, so you sign up for different ones. And that particular one had a pretty rigorous exercise thing before and after, which I thought was fun. And so I signed up for it, fully knowing that in addition to the fun exercise, I had to give the core sample of my muscle. Surprisingly, all of that fine motor stuff, unaffected. Even when you arrive in space, you can do all the normal things with your fingers and just like you said, play musical instruments, pick up tiny things. In fact, that's one of the experiments that I was a part of. We do a bunch of baseline experiment data collection before we launch, so they know what your level of performance is prior to going, and then you do those same experiments when you get back. In some cases, you do them while you're in space, but it's very often not exact same thing. But one of those in particular were some fine motor things and putting pegs in holes, and I found it to be the exact same as when I left. I told my strength and conditioning rehab guys, the first thing I want to do is shoot a free throw when I got back to the gym from landing we land in Kazakhstan, flying an airplane all the way back to Houston. A bus drives us from the airport back to the rehab center, and I walked into the gym and shot a free throw, nothing but net.
No.
I swear to God, you can ask them. So it did not affect my free throw. It would affect my jump shot because the jumping aspect of it, but the free throw is very mechanical and you can repeatable and you can do that. The spacewalk is, in NASA lingo, it's called an EVA, or extravehicular activity, and that's when you put a spacesuit on and open up the airlock hatch and go outside and do some tasks. And we don't do this just randomly or willy-nilly. It's probably a couple times every 6 months do we send some people out to do this. So actions build up, the list of jobs builds up, and it gets put in a job queue, and then we'll go out and do this. What are those jobs? Repairing broken pieces of experiments or hardware outside the space station, or installing new equipment or experiments. Those are basically the types of activities that we're doing out there. Everything that we use on a spacewalk has a little retractable tether to it. A skinny little line, maybe like thick dental floss, and that is what tethers your cordless drill and the bits that go on the end of that, because there's really just two sizes of bolts on the space station, so we do have to swap out sockets. There's other types of tools, and there's tens and tens of them, so I can't kind of go into it, but all of them need to be brought out with you in bags, and every bag is tethered to something, and inside the bags the equipment is all tethered. So tether management becomes the #1 problem on a spacewalk, and keeping your work site kind of neat and tidy. We're all guilty of going in our garage and getting deep into a project and kind of having tools everywhere. That method does not work on the space station. You really need to be organized and put things away, otherwise it's a complete disaster outside. Well, we take out Velcro and tape and wire ties, actually, like a strip of wiring that you'd run in your house. It's usually 3 strands that are in your house. If you had one of those cable 12 gauge metal wires about 2 feet long, we have many of those in a little caddy, because those are super handy to just tie things up and secure things. So those are some of the more simple consumables. Other consumables that we do are kind of like grease. You mentioned that. We do. In fact, there was a spacewalk last week, and that was one of the main jobs of the crew, was to stick a grease gun into the moving mechanism of the robotic arm and lube up all of all the things that move. The spacesuit is pressurized to 4.3 pounds per square inch, PSI, above the ambient pressure around you. So if you put the spacesuit on here on the ground, you actually go to a greater pressure than what we are, which is equivalent to like scuba diving to around 10 or 12 feet. If you have no pressure around you, which is the case on a spacewalk, then your absolute pressure that your body sees is equivalent to about an altitude of roughly Mount Everest, of 26,000 feet or so. And Mount Everest climbers typically breathe 100% oxygen. You know, of course, some don't, but so consequently, inside the spacesuit, we breathe 100% oxygen and are physiologically seeing this high altitude environment. And so we were putting out a lot of exertion into some of the tasks, because quite frankly, a robotic arm can mate 2 pieces of metal, but we are the ones that actually have to tighten the bolts and connect it all. And sometimes when you're dealing with big bolts and electrical cables, they don't really want to cooperate, and you have to put a lot of force in. So there are periods of time when your heart rate really spikes up, and this is bad for the main reason of the carbon dioxide removal system on the suit. The higher your heart rate, the more you're respirating, the more CO2 you're putting into the enclosed environment, and therefore the harder that your CO2 scrubber has to work. And the consequence is it shortens the spacewalk. So if you have a spacewalk that's planned for 6 hours, and you have 45 minutes where the person is working way harder than anticipated, that cuts down the capacity of the CO2 remover by some percentage, and you might only get 5 hours out of the system, and then therefore not get all the job done that you had hoped to do. So we really want to keep an even metabolic rate throughout the whole thing, nice and calm and slow and smooth, but there are some cases where you just have to work hard. I did 3 as part of the shuttle mission and 3 on my last space station mission. And they're generally about 6.5 or 7 hours long, and it's hard work. It's physical labor that you're out there. You have about 32 ounces of water and a camelback-like thing in your belly, no food, and you get in the spacesuit about 4 hours prior to going out. So total, you're inside the spacesuit for about 10 hours, which is a long time for food and bathroom kind of thing. So it's a long day, but 5 of my spacewalks went pretty much as planned. We installed some batteries that were needed replacing. We installed or activated an outdoor experiment platform on the Japanese section of the space station on some of my shuttle EVAs. One of my space station EVAs, there was an ammonia leak outside the space station. Ammonia is part of the cooling system. If the cooling system fails, then a lot of the components, both inside and outside, will overheat. So anything associated with the cooling system is a critical thing that needs to be repaired. So we had to repair this pump. And then on my final spacewalk, myself and Luca Parmitano, an Italian astronaut, we were outside. And early into the spacewalk, about an hour in, he had water dripping or flowing into his helmet. In a nutshell, we were working and on our jobs, and we were about 30 minutes ahead when Luca had called down and said, "I have feeling water." And my first thought was, oh, well, it's going to take the ground about half an hour to figure this out. They're going to tell us it's okay and we'll keep going. But we're ahead half hour, so everything's okay, it'll all be fine. And then I shifted from that thinking to, wow, this is a serious problem, over the span of about 5 minutes, as he and I were talking about the nature of the water, how cold was it, where was the water, at what rate was it filling up. And then when I finally floated over and looked in his helmet, I saw like a half of a softball, half of a grapefruit sized water blob jiggling around on his top of his head, and realized, oh, this is not good, and we just need to hurry up and get back and get in. And the getting in part sounds trivial, but we were maybe 30 meters away from the airlock, and we had both taken different paths to get to that point. And each person has a safety tether, which is a retractable dog leash-like thing that keeps you connected and safe. And so either we had to go back our independent ways to stay on our safety tethers, or one person had to hop over to the other guy's tether and unclip and leave a safety tether out, which is generally bad because that can wrap up in a lot of mechanical moving parts on the space station. So we had to go back separately, and during this going back process is when it got really bad for Luca. He was by himself, couldn't see, couldn't hear. It was nighttime on the back side of the space station. The outlet of the oxygen is right at the back of your head. And so it flows in and kind of goes over your head, the theory being that you want fresh air to come down and continuously flowing fresh air over your face. And the water at first, the surface tension is the strongest force of that water. So the water was sticking to the back of his head, and eventually the back of his head got full, and it started to do just like you indicated and spread around like he was a fish inside a fish bowl. And this was a very bad situation because the water got in his ears and covered his eyes and got in his nose and was close to his mouth. By the time we got back inside and back to safety where we could take his helmet off, it was very close to covering his whole entire head. The spacesuit is like a very thick rain jacket. And if you put a thick rain jacket on and work really hard, you build up a lot of heat and you would overheat. Spacesuit's the same thing. So we have this long underwear with cooling lines woven through the long underwear, and cold water flows through this garment, and that removes the heat. It's a heat exchanger basically for your body, takes the heat away, transports it into the backpack, which then there's a block of ice that's formed at the interface between the vacuum side of the spacesuit and the inside of the spacesuit. This water, warm water, is flowing through this block of ice and returns at just above freezing, like 34, 35 degree water, and then flows over your body. Well, this cooling water the pump that moves this cooling water had a problem where there was crud in the water lines, basically, to use a very scientific term. The crud clogged up some of the outlet holes of the pump, and therefore the water couldn't flow in the direction that it was supposed to, and it had to go somewhere, and it backed up through a way we didn't anticipate and went through backwards in a check valve through into his helmet. And so water that was now mixing in with the oxygen in it that was coming in. So that was the nature of the failure. It really is an awesome job, and I feel very lucky and honored that I get to do it. There's a lot of people that apply, and I was one of them. I remember thinking, after I came home from my interview week in Houston, like, wow, I was there with 20 people for a week, and any of those 19 others would be amazing astronauts. And that was just 1 week out of, I think, 6 or 7 that I was part of. So I really didn't think I had a big chance of getting selected. But to your question, why did I want to apply? I was doing a cool job in the Navy. I was in the SEAL teams, and I learned more and met another SEAL who had become an astronaut, Bill Shepard, and learned about what he did, and actually learned what an astronaut does, other than, oh, they go to space. And I thought to myself, well, that's kind of a cool job, and I like doing hands-on operational things, and it seems like going to space is a very hands-on operational job. And so that's what motivated me to apply. And I applied one time in 2000, or what was the class of 2000, and was not selected. And then there was another class 4 years later that's the one I applied and was selected for in 2004, and that's when I showed up to Houston and started my astronaut career.